for our project, we have chosen to go over the flow simulation within SOLIDWORKS. We'll go up to the options here to the drop down and add-ins. In there you will find the SOLIDWORKS Flow Simulation 2025. I'll click OK there. It'll take a second to load. And we can see here it has a box around it, which that is the computational domain, which will be the area in which we'll have the fluid running. The larger that is, will be more iterations for running the simulation, which you will see later. To start it off, we will go to the Flow Simulation tab, and then up to Wizard, which we'll make a project. Name it there with any comments. Leave the rest the same. Next page we have options for all units that are available. I will leave it as SI, but if I wanted to change any of these other parameters, I can change the units for those as well. So I could do SI units, but keep the velocities in miles per hour for reference. You can change all the rest of these here with the drop downs, so I will leave that. And on the next page, we have the options for physical features you can have for the flow. For ours, we wanted to do an aerodynamics test with, I have an example. I have our wing foil here. And so for modeling a aerodynamics flow simulations, we would want fluid flow to be on, and we also want gravity. So we'll enable that. And here it has the axes in which it's acting, which right now is going down in the Z component, which in our model we would rather have the Y in the negative. So we will change that there. After doing that, we can go down to the exclude internal space. Since we won't have internal features, we just have an external part, and all the rest can stay the same. And on the next page, we have all the fluids available to us from SOLIDWORKS. We can have it go through liquids or gases, and there's an abundance of options. For ours, we will just select air, and then go to the add button. And then we have the flow type that is available. We want laminar and turbulent, since we would realistically experience both in a real life scenario. And we will just ignore humidity for now. The next page is more for thermal conditions, which we will now worry about for our simulation. So we go to the next one, and here we're able to change the velocity parameter, so the speed in which this airfoil will be moving. And for that, we want it acting in the z-axis negative direction. So you can put any value you want there that you are wanting to simulate. And there are other parameters you can mess with, but leaving the rest the same, we'll just keep it simple and still get you the results. So I will click finish here, it'll load. And now I can go up top to the run button up here. I click that, I click run again, and it will run the simulation and give me this tab here. And on this screen we can see the total cells and fluid cells, which will change depending on the size of your part and the size of the computational domain that you size to be. The larger, the more iterations it will be running. And so while that's going, we can include goals that we are wanting. We can select the goals. We do insert global goals, and there's a variety of options for what you would like to display. We have the main ones being pressure, temperature, velocity, and there's forces in each axis, as well as torque. So for an example, we can do the force on the Y, which will be the max. We'll click OK. Now we can alter the results in how they're displayed, and there's a few options here. We have a cut plot, which we can insert here and select the YZ plane. And with that, you can have different display options with the contours, isolines, and other options. And you can also choose the data that will be displayed. In our scenario, we would want pressure. There are lots of other options though. So then I click OK, and we can now see the cut plot of this one section and how the pressures are changing with that flow that we have inserted. And another one is a surface plot, which we just choose the surface in which we want to display our data. And there we can see that surface reaction pressure on our airfoil. And there are also flow trajectories that can act along chosen faces. So if we choose the top and the bottom here, and we will display it with lines with arrows, and I'll click OK there, and we can still see that pressure gradient along our airfoil here. And then there's also an option to play this flow. And now there are other options for displaying the data, but those are the three biggest ones in which you would want to summarize your data. And to view the results, we will go back to the run, and then we will insert and have a goal plot and select our Y force. And there we can see that initial lift that we're getting is around 53 newtons. And this will change depending on the velocity of your flow and the shape of your airfoil that will be shown in the following section of the video.
This is the results section of our video here where we actually conduct a flow simulation on the glider that we've created here. And I've created 3 different configurations for the glider, being symmetric, flat, and cupped. And we're going to want to analyze the lift force and the drag force that are being exerted on this aircraft that will, essentially allow us to rank these airfoils in order of efficiency and which we would want to maybe choose for our design. So to analyze something meaningful here, I've created a surface plot by selecting each of the surfaces on this aircraft that I want to know information about here. That's going to give us the corresponding pressure distribution on this aircraft. So as you can see up here in the top left, we have our pressures and the corresponding color scheme, and we can see on this aircraft that the colors do not really change on either side of this wing, meaning the pressure distribution is roughly the same. So just to get some initial parameters out of the way that I've selected, by the way, this aircraft is moving at 30 miles an hour. There's a 30-mile-an-hour wind moving in the reverse direction, and the force of gravity is turned on. And if you want to look at this pressure distribution in more detail, we can also look at a cut plot of specific sections of our wing here that shows us really where the main pressure zones and the direction of airflow will occur here in the cross-section area. So as we can see here with the symmetric wing, really not much of a difference. There should be no difference on either side of the wing. It's fully symmetrical. That only difference might be due to gravity and how that's affecting the actual air. So let's hide that. And now we can look at our next one here. So here is the flat version, and this has a contour plot on it. And if we look at the underside here, we don't see this blue lower pressure side here. We only see it on top. So that means there's a higher pressure on the bottom, which is what we want in the case of an airfoil if we want to generate lift. So here, if we look at the cut plot here, you can see some of this got caught. Really no difference there. Not generating any lift because that's flat. But here we see a noticeable low pressure zone on the top side of the wing that is now generated. And last but not least, we have this cut plot, cupped airfoil surface plot here. And looking at the cut plot, we see this different type of distribution as compared to the flat wing, but still a lower pressure zone on top. So we know that this is creating some form of lift here. Okay, so if we want to look at the results here for the lift force and the friction force of each of these aircraft, let's start with the symmetric one. We can look at these goal plots, which I can just create by right-clicking, inserting a global goal that we're looking for, running the study. Once the study is run, you insert whatever plot you want to look for here. So let's just go to the one that we already have, and this will show us the corresponding drag force. So let's find out which of these has the highest amount of drag and the lowest amount of drag. Right here, this has an average value of negative 0.018. Go to our flat, show negative 0.02, a little bit higher. And we go to our cupped, show our friction force, negative 0.019, which is a little bit less. So this one's right in the middle. So now we know the symmetric has the least amount of drag and the flat has the most amount of drag. Now, if we want to look at the lift, we can look at our other goal plot here. This is showing us the net force in the y direction, which corresponds to the lift. Boom, our average value here, 0.014. That is very low, almost no lift. We look at our flat, show this, 0.439 pound force. It's pretty substantial. That'll keep it afloat and resist gravity pretty well. And last but not least, we have our cupped, 0.455. And so those are ranked from least to most lift, symmetric, flat, cupped. So if you want to choose the airfoil here with the least amount of drag but the most amount of lift, you would want to choose this cup design. That concludes our glider study.